I'm Rajesh. I'm from Singapore Management University. I'll be your lovely session chair. This session is going to be on everything and anything related to accessibility. The talks are going to be on, well, 3 of them on sign language, so that's clearly of high interest. Another one is going to be on video conferencing. And the next talk is actually going to be on improving applications for people with low visibility, actually. So, yeah, so the whole point of this is how do we make our systems, our applications, our technology more accessible to everyone, right? And everyone is really a very hard word because people come in all shapes and sizes, right? And trying to figure that out is actually really hard. So let's see what we can do, right? So without any further ado, I'm going to start the talks, and then we'll have time for panels. So the panel will hopefully be very interesting because I want to make it more interactive, right? So usually panels, only the speakers are talking, really boring. I want to get the audience involved as well. Okay, so we'll see what we can do. Okay, so next talk is actually going to be presented by TOUHID. Can you set up? Right, he's a grad student at Penn State, right? Yeah, so he's a grad student at Penn State, and he's going to talk about how do you actually make your smartphones more accessible to people who can't actually see that well, right? We take the interfaces for granted, but as you all know, they're tiny and they're very small. So how do you actually fix all of that, right? So he's still setting up, so I guess okay, hang on.
Hello everyone. Today I'm delighted to share present our work on SpaceXMag, which is an automatic, scalable, and rapid space compactor for optimizing smartphone app interfaces for low vision users. I'm sorry for the big name. I'm TOUHID. I'm a third-year PhD student at Penn State, and my co-author and my advisor is Dr. SYED. Low vision is a spectrum of vision impairments that cannot be fully corrected by glasses, medication, or surgery. Individuals with low vision can lose the peripheral or central vision, or have blurred vision, extreme light sensitivity, tunnel vision, or near total blindness. Users with low vision have difficulty seeing small texts or icons on computer screens. The situation is worse for mobile screens, which have smaller form factors and smaller displays. Hence, they use screen magnifiers. Screen magnifiers magnifies content uniformly, generally speaking. Here is a sample UI of a smartphone on the left, and here is what the same UI would look like with 400% magnification on the right. And the view a low vision user gets is also drastically different. It's not just about the visibility. The view a low vision user gets is also drastically different from those without low vision. So how would a user with advanced diabetic retinopathy, which is a prominent low vision condition among low vision users, use the UI on the right? So let's take a look. This is a simulated condition using the ViaOpta app. So let's take a look. So the user is trying to navigate into the settings menu, maybe trying to look for some options. Now going down. And now the user is lost in white space and not knowing where they are on the screen. Okay, so let's talk. With uniform magnification, which is magnifying content and white space alike, context gets lost, specifically around this area as marked by the yellow marker. And users have to do excessive zooming and panning. As such, the experience is tiring and error-prone. To address these issues, we propose a SpaceXMag, a fast automatic user interface adaptation framework. Now let's look at the same UI being used, but this time the UI is being optimized by our proposed framework first. It's on the right. On the left, you can also see the original UI that was being used. SpaceXMag performs a nonlinear optimization and magnifies UI content and white spaces differently, something known as differential magnification. So this is how differential magnification works. Consider this UI where we have both white space and text content. Now I want to get rid of the white space, so what I do is I take the white space and magnify it by something like 0. And then I take some text content and magnify it something by greater than something 1. Then this is what I get. So this would be the main idea of differential magnification. Now the ideas of differential magnification in UI adaptations is not really fresh, and I'll discuss 2 very relevant such prior works, starting with steering wheel. Steering wheel dynamically adapts web pages to reduce white spaces inside certain UI elements, as you can see the before and after images on the screen. However, Steering wheels algorithms is ad hoc, and the idea was demonstrated only on web pages where one would have readily access to the page's source code. The second work is Supple, which is an early optimization-based UI adaptation framework. Supple used user inputs and tried all possible combinations of a UI to find which one is more adaptable, more usable for a certain user. So this is the before and after layout looks like. And again, with Supple, was quite slow due to the exhaustive search and also needed instrumented graphical user interface framework. SpaceXMag overcomes the limitations of the prior tools. Here's how. Compared to steering wheel's ad hoc process, SpaceXMag has a defined and automated process, and while steering wheel was only demonstrated on web pages, SpaceXMag would work on any UI as long as the underlying meta representation is available. The generalizability of SpaceXMag is demonstrated on the RICO-SC dataset, which has around 25K screenshots of Android applications. Compared to Supple's slow execution time, which can take up to 13 minutes in worst case, SpaceXMag would take 6 seconds, even in the worst case. And while Supple needs instrumented GUI framework, SpaceXMag does not. Now let's take a look at how SpaceXMag works. There are 3 major steps involved, and they're DOM tree construction, constraint formulation, and objective formulation. So let's get into those. The first is DOM tree formulation. DOM tree is the tree-like hierarchical representation of an application of the items in the UI. It plays a crucial role in formulating constraints and step-by-step optimization of SpaceXMag. So let's look at a demonstration. So at the beginning, it's just N1. Then we have the 2 children of N1, N2 and N3. N2's 2 children is N4 and 5. N3 has 1 and 6. And this completes our DOM tree. So the application is on the left, and you can see the DOM tree on the right. The second step is constraint formulation. We can't just let items move around the UI without posing some constraint. For example, this modification on the bottom inside N2 is not allowed because a child node must stay inside its parent. And relative positions of the children within a parent must not change. As such, we cannot swap the positions of N4 and N5. Now, there are many more constraints that we apply during SpaceXMag optimization, such as for alignment. The paper has extensive details regarding those. The third step is formulating an optimization objective, which is to minimize the cost for all the nodes. For every node Ni, the cost is given by the equation as shown on the screen. I'll simplify what the equation means. The cost is equivalent to the white space inside a parent not occupied by children, as shown by this animation. The process of optimization is bottom-up in the tree, meaning a child must be in optimized state before the parent can be considered for optimization. We use a nonlinear Python optimizer named Gecko for SpaceXMag. Now, let's look at the step-by-step optimization of SpaceXMag. So we start off with original UI, where a JSON file is probably providing the metadata. Then we plug in those metadata into the UI and get the bounding rectangles. Now we have the tree. Then, at the first step, we only optimize the leaf nodes. Then we get into the parent nodes. For example, 7's parent 2 is optimized next. Then we can do 4, 5, 6. Let's pick 4. Then 5, 6. Now that all the children of 1 are optimized, 1 can be optimized. So this is what we get. We then resize the optimized UI back to its original shape and gain some magnification in the process. Finally, we draw some highlight rectangles around the identifiable UI objects to make them more visible to users with low vision. So here is the first and final version of the UI. And this would also be a good place to explain the name of our framework. We strive to save space and ended up getting some magnification in the process, making the name SpaceXMag. So we also evaluated the usability of SpaceXMag generated UIs with 11 low vision users. The participants performed 2 different tasks. One was overview task and target locating task. They did those tasks using 3 different magnification modes, as you can see on the screen: full screen, window, and fisheye. The paper has extensive details regarding this. Please read for more details. So for the overview task, the participant's task is to just look at an UI and tell us what this was about. For example, if an UI was given, they would report an email text field, a password text field, and a login button. And then we normalize the completion time using the number of items they successfully managed to report. Our results show that SpaceXMag, the difference between participants' performance in original SpaceXMag UIs were statistically significant in all 3 magnification modes. Generally, on average, SpaceXMag around 28% time. Then for the second task was looking for a specific target in the UI, such as the login button here. Then the completion time again was normalized by the total items in the UI. Again, we found a statistically significant difference for all three magnification modes for SpaceXMag against original UIs. On average, it was around 43%. Throughout the study, we had many encouraging feedback from our participants. Participant here mentioned that I felt more confident navigating the screen-optimized UIs as I was less afraid of losing information on the screen. I also felt that the choice of magnification mode was not as important with the optimized UIs. We report many more insightful findings in our paper. To wrap up, uniform magnification in UIs causes a lot of loss of context, necessitates panning, and the user experience remains tiring and burdensome. To address this issue, we introduced SpaceXMag, a differential magnification technique, which is fast, automatic, and scalable. Human subject study shows that SpaceXMag can improve the user experience of low-vision users in smartphone UIs. Thank you for listening to this presentation, and I'll be happy to take questions.
Thank you. One question?
Hi, Jennifer Rhoda. I'm a low vision professor from the University College London, and this is really important work speaking to someone who can't see well enough to use the UbiComp app. I do think, though, it's really important not to lump all kinds of visual disabilities together, and I was curious what sort of variety you saw in your data for people with different types of visual disabilities. Thank you.
Thank you for the question. So when running the study, we did notice some differences based on the low vision conditions of the users. For example, you notice the fisheye magnification mode I mentioned. We found that users who sit very close to the displays were more bothered by the fisheye's distortion. And we also found that the window magnification mode is something they preferred. And as for users based on different conditions, I would say, yeah, we saw some users who were comfortable using 200 to 300% magnification on different UIs. And we saw some users who were struggling to see the items, even with 800 or 1000% magnification. So, yeah. I think, yeah. For example, at higher magnification level, the full screen magnification, which is just uniform magnification, was more tiring as the distraction or getting lost in content is higher. And more likely they preferred just the window or fisheye magnification mode in most cases.